email with more information about it. If you have any question during the webinar, please feel free to use the chat and we can go over them at the end. We will have a space for questions. Also, feel free to provide any feedback in the chat. And remember to keep your microphone and camera muted so we have more organized the event. You can also turn on your mic or camera at the end when we have the space for questions. Now I would like to introduce our speaker, Moataz Eldib. He is a senior technical sales engineer at Shaeffler, specializing in automotive, industrial, and in hydrogen fuel cell technologies. He has over 20 years of experience in product development and engineering, and is also recognized for his leadership in the hydrogen and fuel cell industry. Moataz oversees the strategy and execution of innovative products, ensuring they meet the evolving needs of global customers. His career is marked by successful leadership of cross-functional teams in complex projects across multiple continents, applying best practices in product development. Moataz also excels in understanding and analyzing customer requirements and market trends, and effectively communicating them to stakeholders. He holds a degree in mechanical engineering and has advanced certifications in business administration and project management. He's also committed to driving product innovation and contributing to a sustainable and efficient energy future. So now I would like to turn it over to Moataz Eldib so he can continue with his presentation. Thank you, Moataz, for being here today. We're excited to have you.
All right. Yeah, thank you for the introduction and the opportunity to present. So I'll get right into the presentation. So we'll start with a little bit of an overview of Shaeffler and then look at specifically electrolyzer technology, as well as the hydrogen market and federal policy, and then pathways to sustainability, along with maybe 3 example projects that can maybe prompt discussions and give you some ideas on how hydrogen can be implemented in manufacturing operations to reach sustainability goals, along with some maybe recommendations and high-level suggestions on engaging in projects. So to start, Shaeffler is a global company that's been in business for over 75 years, headquartered in Germany, and our product lines are in automotive and industrial components. So we've got over 83,000 employees worldwide with locations around the world, including our industrial headquarters in Fort Mill, South Carolina, and our automotive division in Worcester, Ohio. So Shaeffler, our products are in just about everything that moves. So mobility is kind of the core element of the product lines, from on-road and off-road vehicles to aerospace to the wind energy segment. Our products are present in many different applications. So if you're not familiar with Shaeffler, or if you are, you know, Shaeffler is a bearing company. So how does a bearing industrial and automotive company get into hydrogen technologies? Well, as I said, our motion is our connecting element between our product lines. So whether it's guiding motion to driving to energizing and sustaining motion, our product lines are organized in a way that we can build upon our core competencies and our expertise to create valuable solutions for our customers. So under the Energized Motion product line or product family, we've got our hydrogen fuel cells, hydrogen electrolyzer, and our bipolar plate business. And that business is really well suited to the core competencies of Shaeffler, where we are very good at cold forming and stamping metal, highly engineered specialty coatings, injection molding for gaskets and seals, and then complex system expertise. So that is really the competencies that make us very well suited to be involved in the hydrogen industry through our bipolar plate manufacturing. So the bipolar plate is the core component of a hydrogen fuel cell or an electrolyzer. and we can make those products with a high level of precision and quality, and at very high volume. So, which are needed for the hydrogen industry. So maybe a little bit specifically about electrolyzers. So the electrolyzer is a device that will take in water and uses electricity to separate the water into hydrogen and oxygen. And in the market today, there are three core technologies that are readily available commercially: alkaline, PEM or proton exchange membrane, and solid oxide electrolyzers. So the PEM is where Shaeffler is at the moment, where our product line is. But we'll start with alkaline, where it's a very mature technology that's been around from the 1850s, and it has some definite benefits where it is typically attached to a hydroelectric dam to produce a lot of hydrogen, where it's got a very stable electrical grid or electrical input from the grid. So it's a mature technology that's been around for quite a while, but it does have some disadvantages where it's got a large footprint, low dynamic range tolerance, long startup times, and maybe a bit lower hydrogen purity than some of the other solutions. Moving to the PEM, which was a more recent development where trying to solve some of the challenges with the alkaline electrolyzer, where you want to get a more compact footprint and you want to be able to operate with more dynamic range of electrical input. So this is a technology that's really well suited to connection to renewable energy, where it may be a bit more unpredictable or variable input. So the PEM technology can really tolerate that and still have a good level of performance and efficiency. And the other benefit of the PEM is that the hydrogen's coming out at a little bit higher pressure at 30 bar, but 350 bar is possible. And it does have the advantages of a quick startup time and again, the compact footprint and high purity of hydrogen. Some of the drawbacks of that technology, some higher material costs where we're starting to use platinum group metals and iridium in the catalyst membrane, as well as a corrosive environment, and maybe being a bit newer in the marketplace. The overall lifetime of the system is still to be determined. And as we get to more I guess, recent developments in electrolyzer technology, we've got the solid oxide, where it has very low-cost materials, very simple catalyst and membrane, but it's operating at a very high temperature. So at 700 degrees Celsius, it does have the benefit of having the possibility of high efficiencies, but it does have longer startup time and less tolerant of dynamic range of electrical input. So all three technologies have the same basic operating principle, where you have an anode and a cathode. You've got a separator or a medium in the middle that with a catalyst, and you have electricity input, and the output is hydrogen and oxygen. So those operating conditions, whether it's temperature or pressure, as well as the current density and electricity input, are all the different characteristics of the system that would make them appropriate for one application or another. But typically in the United States and in most global installations, the alkaline or the PEM electrolyzer are the dominant technologies. So looking at the hydrogen market in the United States, there is 11.4 million metric tons of hydrogen produced and consumed annually in the United States across a variety of applications. And most of that hydrogen is produced from fossil fuel or carbon-intense sources. So only about 4% of the hydrogen produced in the United States is coming from renewables. So it shows that there's a lot of potential to decarbonize the hydrogen supply chain. And across industries, hydrogen is used primarily in the oil refining industry, typically to desulfurize diesel and gasoline, as well as in ammonia and methanol production. So there is some applications in metal processing and some other applications such as transportation. And hydrogen is a very versatile element. It can be an energy carrier, it can be a fuel. And what this is showing as part of a national clean hydrogen strategy and roadmap is that there is a lot of different applications for hydrogen to be used and a lot of different pathways for hydrogen to be generated, generated, and it can be from renewables, from some fossil fuel sources, and utilizing the existing grid and infrastructure that we have today. So that versatility can be used to give us multiple pathways to decarbonize. So whether we are decarbonizing the existing hydrogen at scale production, using it as a transportation fuel to replace fossil fuels, or as an industrial feedstock, we've got opportunities to decarbonize, and this graphic is showing where there is a good or higher potential for hydrogen to decarbonize, and where hydrogen is being used at scale today. So in the chemical and refining industry, it's really being used there at scale, and we've got a good possibility of hydrogen to decarbonize heavy transportation, some rail, and some light commercial vehicles, as well as iron and steel and cement production. Some of the other applications may be a little bit less promising, or not as easily implemented with the hydrogen solutions today, but there is some easy pathways or easier pathways that hydrogen can be used to decarbonize the industries today. And to support those strategies, we've got a number of federal programs. We've got the Infrastructure Investment and Jobs Act. We've got the Inflation Reduction Act, where the federal government is supporting this clean hydrogen strategy through research and development grants, funding for projects through tax credits or grants, and also production tax credits. So the target is reaching $1 per kilogram by 2031. And the need for hydrogen to decarbonize and reach the decarbonization goals of the United States is having an additional 10 million metric tons of hydrogen per year added through, that is green hydrogen, mainly produced by electrolyzers. So it's a very ambitious program where the federal government has really taken a lot of aggressive action to support it. The other aspect of the support is these hydrogen hubs, where there are networks of hydrogen producers and consumers spread throughout the country to encourage the development of projects, as well as matchmake with the people that are demanding hydrogen and putting them together with the hydrogen sources. So already, and this is a bit dated, but as of the end of 2022, based on the Department of Energy Commercial Liftoff Report, there are more than 3 gigawatts of electrolyzer projects that have been installed or about to be commissioned in the United States, as well as 60,000 fuel cell powered forklifts, a few buses on the road, as well as some cars, but really the electrolyzer and the forklift markets seem to be the strongest in hydrogen so far. So on the topic of sustainability, tying it together with some of the initiatives that a lot of companies are going through, the ESG regulations, and trying to measure and monitor the greenhouse gas emissions that a company has because of their operations. This is usually through the methodology of measuring the scope 1, 2, and 3. The scope 1 direct emissions, whether it's at the facility or transportation, and then the scope 2, the indirect energy purchases that a company does. So this is really a good starting point for starting to think about how sustainability initiatives can be implemented and how hydrogen can be used to eliminate some of those carbon emissions. So like a lot of companies, Shaeffler has some very aggressive and ambitious goals toward climate neutrality. So we've got a sustainability report that's available, and we have a goal of being climate neutral by 2040. And there's three main pillars of that strategy. One is, sustainable materials. So part of that is committing to being an off-taker for green steel. So hydrogen is a big enabler for making green steel, so we can provide the hydrogen technology for some of our vendors to implement some of these initiatives, and then we can commit to using this green steel in our own processes. So we use a lot of steel in our products. So this is can be a big step into that toward that sustainability goal. And then in our production, we've got 46 plants around the world that are using 100% green electricity, as well as trying to have goals to reduce our water consumption. And then in our product lines, we are, besides the hydrogen technology, we are involved in the electrification of the automotive industry through some of our product lines, and also implementing innovations in our bearing product through friction reduction and other innovations. So some examples that may be appropriate to your applications, or might give you some ideas on the pathways others have taken to get into to reduce their carbon emissions through hydrogen. One of the main applications is the forklift. So there's a lot of history with implementation of hydrogen-powered forklifts in different facilities, whether it's manufacturing or distribution. And this is a bit unique example where maybe the forklift itself may not directly contribute to the scope 1 emission reduction, but it does have a very strong business case to justify hydrogen at a facility. So the challenges that are trying to be solved for in the forklift, besides energy, is productivity and labor and space savings, where there are challenges with battery electric vehicles that are being used, or trying to convert from internal combustion forklifts to electrification. And hydrogen provides a very strong business case where it can alleviate some of those challenges with labor and space associated with maintaining and changing batteries for electric vehicles, keeping the productivity up of the vehicles, and then being able to scale efficiently when the operation requires it, that may be more efficient than battery electric vehicles. And with these applications, there are opportunities for getting green hydrogen, whether it's on-site generation or delivered hydrogen. And the forklift is the starting point for a lot of the parallel applications that you see around a manufacturing facility or distribution center, where maybe the business case is not as strong, say for support vehicles like sweeper scrubbers, terminal tractors that run on site, to delivery vehicles, refrigerated trailers, and even backup power. So maybe the business case is not as strong for these individual applications, but once you started with the forklift application, it can help make the business case for these other applications to get you on a path to emissions reductions. Another example application in power generation. So this is Duke Energy is starting to commission a hydrogen-fueled peaking power plant in Central Florida. So today they've got over 74 megawatts of solar energy capacity at the solar farm. They've got gas turbines that are powered by natural gas that they're using for grid balancing and peaking. And they wanted to have a way to decarbonize. And one of the challenges is that are the renewables uh, as um, uh, as as available as the fossil fuels that they're used to, and can it cycle quickly and be turned on quickly and available when it's needed? So, having a solar energy maybe tied to a battery is a good application, but maybe the battery is not as responsive. And in this application, what they can do is they take the 2 megawatts of electricity from the solar farm, generate hydrogen. They can store 2,500 kilograms and then use it in one of their gas turbines and put 83 megawatts back onto the grid. So this can cycle very quickly because the hydrogen is there and available. And it is a way to decarbonize and still maintain the integrity of the application and the benefits of the fast peaking power. And then one of our own applications at Shaeffler, we are installing and commissioning our own system in Schweinfurt, Germany, where we have a 1 megawatt electrolyzer generating about 450 kilograms of hydrogen per day. It's tied to renewable energy that's available from the local grid, and we can store that hydrogen in a buffer tank and then make it available to our heat treatment furnace that is a hybrid furnace that can be powered by natural gas or hydrogen. So when it is using the hydrogen, we are eliminating about 5,000 tons per year of CO2 emissions. So this is where a chance for us to use our own technology and showcase it and offer it to as a solution for decarbonization to one of our own sites. So I guess a few key steps when thinking about hydrogen and the decarbonization and manufacturing. It's really important to understand scope emissions. So you can't change what you can't measure. So having a comprehensive assessment to establish a baseline is a key step. So you really need to know what the sources of emissions are and where you can start thinking about reductions and implementing the technology. And then aligning stakeholders and getting buy-in early. So a lot of the corporate sustainability goals are requiring a collective effort across stakeholder functions in the company. So it's really important that getting people aligned and understanding how to implement these projects early on is a key step. There's ambitious federal programs with funding and complementary state and local funding. So this is really highlighting the economic and environmental benefits of hydrogen and as a pathway to decarbonization. So those programs are available and need to be can be fully taken advantage of. And then finding partners in your area. This is to aggregate hydrogen demand, but sharing the risk of a project, diversifying the project application, whether it's for forklifts or power generation or other processes. Having a diversity of applications can really help with sharing the risk and creating collaboration and learnings to strengthen project viability. So hydrogen can really drive transformative change to decarbonize manufacturing, and it's a good complement to other green technologies. So I guess a final thought on Shaeffler. So we are definitely the right partner to work in the scale up of the hydrogen economy from our mass production expertise, global footprint, and knowledge of the core technologies. We're really well positioned to be part of the hydrogen economy scale up. And that takes me to the last slide, and I think one more slide. That takes the last slide, and I guess I'm ready for questions.
Any questions? This is a great moment to take advantage and ask anything to Moataz about the presentation. You can use the chat or turn on the mic.
I think I saw a hand raised, so.
Yeah.
Yeah, go ahead, Mike. Yeah.
Hey, thanks. What's the smallest electrolyzer technology that you provide? I've got 4 annealing ovens that use hydrogen as an atmosphere, and I'm looking to get rid of my natural gas.
Mm-hmm. Yeah, it's a great application. So in our product line, we've got a 0.5 megawatt electrolyzer. It's really part of our megawatt line, but we're working in blocks of 1 megawatt, where it's a bit more cost effective for manufacturing and implementation. There are in the nice thing about the PEM technology is we can really get down to about 50 kilowatts, but those are typically more lower production volumes and maybe more for research and development. So a 1 megawatt electrolyzer will get you about 400 kilograms of hydrogen per day, and then you can scale up from there pretty easily.
Do you have a relative size of a PV system, given the fact that it's a good solar source in my area?
Okay. Not really. I think you have to look a bit deeper at the applications. So there's a lot of, like in the case of that DeBerry, Florida application, they've got a total of almost 75 megawatts of solar, and they're taking only about 2 megawatts per day from that to generate the hydrogen that they need to have enough buffer storage for the gas turbines. So I would probably say that sizing the PV to be a bit larger than the hydrogen that you're trying to generate, would probably be the ideal way to go.
Great, thanks.
We have another question in the chat. What are the main barriers preventing widespread use of hydrogen in transportation and heavy industry?
Good question. So yeah, typically it's been the availability of hydrogen, and particularly green hydrogen, at enough scale and cost that is not necessarily parity with the incumbent technology or incumbent fuels like diesel, but it's been availability. So as you saw, the hydrogen is produced at quite a bit of scale in the United States, but maybe not necessarily where it's needed. And particularly for transportation. So it's typically been the availability of hydrogen, and then on the transportation side specifically, it's usually been the availability of the vehicles. So there's maybe one company out producing hydrogen Class 8 vehicles now, and some of the larger Class 8 or heavy equipment manufacturers are just starting to electrify their fleets, which is the first step to the hydrogen high fuel cell electric vehicle. So that other aspect is the availability of the vehicle itself. And I guess in industry as well, there's been other, headwinds in terms of the cost of the technology and some risk aversion. But I think the hydrogen hubs, the funding that the federal government has put together, alleviates a lot of those issues, and hopefully makes it a bit more straightforward to implement projects for those heavy industrial and transportation applications.
Thank you. We have another question here in the chat. Can you speak to the energy, pressures, and temperatures needed to liquefy vaporized hydrogen?
Uh, okay, yes. Yeah, for the hydrogen coming out of the electrolyzer is going to be gaseous, and then in a lot of cases, the supply chain in the United States is really organized around liquefaction and transportation of the hydrogen as a liquid. So it's a bit more volumetrically efficient to transport by trailer. So there is a bit of energy input, and I am thinking off the top of my head, but it's not a significant energy input as generating the hydrogen in the first place, but it does require, energy input, and it could affect, the overall carbon balance of the green hydrogen. So typically, the best, most efficient way of implementing the green hydrogen is using it as a gas and keeping it in that form. And for transportation applications, it does need compression from, to 350 bar, and typically that energy input is relatively low. So, yeah, so the liquefaction can require uh, significant energy if it's done at very high scale, but typically the other pathways to maintain, the decarbonization of hydrogen is, keeping it as a gas and transporting it, through pipeline, or using it, generating it close to it, the site of usage.
We got another question. Are there any concerns about storing hydrogen due to its flammable nature?
Yes. So hydrogen, as most other energy sources or fuels, is flammable, and much like gasoline, diesel does require awareness of the risks and adherence to safety protocols. So there's been significant work in the regulatory and analysis side of hydrogen. So there is NFPA 2, which governs a lot of the hydrogen storage and infrastructure associated with facilities. So that has been through a number of different revisions and recognized by, Factory Mutual and other insurance bodies that work in the industrial space. So hydrogen does have some unique properties. It is the lightest element that we know of. So it does, if there is a leak, it does disperse and rise quickly. So unlike gasoline or diesel, where if there is a leak, it can stay flammable and explosive relatively far away from the leak source. Because hydrogen disperses so quickly, it does have the ability to be a bit have a different risk profile than the gasoline and diesel or fossil fuels that we're used to.
Thanks for that. Is there any other question in the audience? Right. I don't see questions in the chat. Moataz, do you want to add anything else? Or I see another question here. Any further comments on forklift?
Yeah, I mean, that's my experience has been a lot of different projects in the forklift segment applying hydrogen fuel cells, and it's been a very successful application. It was one of the earliest funded hydrogen projects, and I think it was because the technology was available. There was availability of hydrogen at the facility level, and so hydrogen infrastructure could be installed. And then the business case was made based on not only the some of the sustainability issues, but mainly the challenges associated with operating battery electric forklifts in a facility. So for manufacturing, floor space is very critical. So trying to add the battery and charging infrastructure to a facility can be very difficult. So the hydrogen fuel cell application of the forklift really solved a lot of those problems, as well as a lot of applications that had internal combustion forklifts and were hesitant to convert to electric, where they were concerned about performance degradation or loss of operational efficiency. So, fuel cells really solve that problem. So I think it's a great use case where the technology is solving some very specific operational problems, as well as giving benefits that can help on the sustainability side, as well as other applications.
Thank you. We have one more question. Who makes the H2 models?
H2 models. Sorry, maybe if you could clarify which models. Oh, gaskets, rings, etc. Yeah. So because again, hydrogen is a bit unique, we have to pay attention to the sealing mechanisms within fuel cells and electrolyzers. So it's typically not the basic rubber seals. So it's a lot of nitrile and Viton, I believe. So it's material that can handle the smaller molecule and is a bit tolerant to hydrogen embrittlement. So it's definitely something that has to be paid attention to in the development of the technology.
So I see further questions here. So they were asking for who makes the forklifts, the hydrogen forklifts, I guess. That's what he meant.
Okay.
And
It's related to the forklift question. Okay, yeah, I saw in the chat there was the seals and the okay, yeah. So there is one of the main suppliers in the United States is Plug Power that are providing the hydrogen fuel cells for a variety of forklift OEMs. So if and then there's another company, smaller company called Infinitium, and Nuvera Fuel Cells, as well as a couple of companies in Europe that are providing hydrogen fuel cells. So there are a few choices out there, but if you've got a standard forklift, battery electric, typically if they're less than 5 years old, they can tolerate conversion from battery to fuel cell.
thank you. I don't know if you read this question fully. It says what materials of construction and associated gaskets, rings, etc. for storage vessels and associated piping should be considered to prevent loss of hydrogen. Are there any material compatibility issues? Any limits on how much hydrogen can be stored in any container or tank, large volume necessary to provide comparable energy by other fuels?
Yep. Yeah. Okay. Good question. Yeah. So I think I answered part of that. So not only in the fuel cell and the electrolyzer is there a concern about the material and the sealing, but also the material that is transporting the hydrogen. So typically the piping is stainless steel piping. And it really depends on the pressure, but the stainless steel is usually, I think it's the 316, but I'll have to double check on that. But the stainless steel is typically what's used. Brass is not compatible because of the hydrogen embrittlement. So hydrogen is, such a small molecule. It gets into the at the molecular level in between. Some of the material itself, and over time can weaken it. So stainless steel is the accepted material for the piping and steel for vessels. And then it really will depend on the pressure. So, there's a very good references within the ASME code for the vessels, vessel construction, and then of course the piping and that is required is all subject to the ASME standards. The limit on hydrogen storage usually is associated with levels of maximum foreseeable loss. So if you're using hydrogen in a building, there is a calculation based on the volume of the building versus the hydrogen that's present. And again, it's all associated with that leakage and dispersion of the molecule to make sure it stays below its flammability and explosive limit. Storage vessels typically are designed around the ASME standard and the pressure. So the size of the vessel is typically for there is a practical limit on the sizes, but it really would depend on the pressure and the arrangement that you've got for storage. Let's see, can be stored anyone? I think that answered the question. I think so. So yeah, if I didn't, please add more in the chat and I can clarify whatever wasn't clear.
Sure. Also, we have your information on the screen. If anybody would like to discuss further anything with Moataz, he has shared his contact. There's his email. And we have a few minutes more for any other question. If not, we will wrap up the session. All right, I don't see any questions in the chat. So we would like to wrap this session and just thanks Moataz for sharing this information with us today. Very valuable. And let's see if we can share the last slide. Please follow us in our social media. Stay tuned for more events. On LinkedIn, we tend to post frequently the upcoming events. You will get the presentation in your email. Thank you so much again for staying with us this afternoon. Have a great rest of the day.
All right. Thank you.
All right. Bye-bye. Thank you.
Thank you.
Bye.